right, so this will be the last of what we'll call the introduction to refrigeration. If we go through a brief walkthrough of what we've talked about so far, again, 4 major components, drew our PFD, have a decent understanding of the assembly of these 4 components, what's happening to the working fluid. We built our ideal cycle, understanding the importance and also the limitations of these assumptions in building this ideal cycle. We looked at diagrams, different plots. We looked at the phase diagrams we talked about R134A, but really these phase plots aren't for R134A. They're more so just generic phase plots and kind of giving you the resemblance of what it should look like. Same thing for pressure enthalpy. And we also went through and constructed a system diagram on the TS diagram for kind of qualitatively what this refrigeration cycle should look like. We also left the pressure enthalpy diagram for you to do on your own. The last portion that we want to get into is looking at the energy balance associated with this system. Now, traditionally in chemical engineering, we would also talk about a mass balance. However, given that this is a closed system, we're assuming no mass enters or leaves the cycle. So really the only importance here is the energy balance. Now I'm going to use a blue marker since the board has become quite messy, so you can clearly distinguish between the energy balance information and all the information we've already gone over. Before we start drawing our system boundaries here, I want to draw out or write out the equation for the energy balance equation. I'm going to write it out and then I'll explain what each piece is. So here's our generic energy balance equation. Over here what we have is the accumulation of energy per unit time. In most, at least lower level classes in chemical engineering, you always assume steady state. So what winds up happening to this term a lot of times is we assume that it's 0. If you get into process controls, once you get into that level of coursework, this assumption here really doesn't become valid anymore. Your process control dynamic models are really focused on the time variable. So in any event, for now, we'll assume that this is a 0. Right here, what we're looking at is the change, this D right here, that's change, so differential change in enthalpy between 2 different points. What we're looking at right here, so this is the internal energy change here of the system. This is the kinetic energy change. Notice the m1/2 v squared. This right here is the potential energy change from the gravitational potential energy. This term right here is accounting for heat exchange or energy loss via an exchanger, dq. And the change in work is either work done by the system or work done to the system. For instance, the compressor is an example of something that's doing work to the system. Whereas if we had a turbine up here, which we don't, we have a valve, but if this was a Rankine cycle, refrigeration cycle that is, we would have work being done by the system to the surrounding. So if we do some other simplifications here, at least for our examples, we're really not going to consider the kinetic energy change of the system. We're also, at least not for our base case here, going to really consider the gravitational difference, but depending upon your system and your plant, if you have a refrigeration unit that goes very high up, maybe to an overhead condenser or something that's on a tall platform, this could potentially become not negligible anymore. So when we reduce down our equation, the equations that we're going to be using here to evaluate this, will look something like this. So we're really going to be only dealing with changes in internal energy, heat transfer, and work input to the system. And that's what we have here, right? We have work being put input, and we have heat being transferred. So let's draw a system boundary at 4 different, and basically label out 4 different systems here around each major piece of equipment. We'll call this system boundary 1. Call this system boundary 2. Call this system boundary 3. Call this system boundary 4. Now what we're going to do is start to develop equations for the energy balance for system 1, system 2, system 3, and system 4. However, because I'm running out of room here, I'm going to erase all of our diagram stuff here. I'm also going to erase some of the state information right here. I want to erase this just to give me some more room while I'm going through these energy balances. So let's look at system 1 and write an energy balance around that. So system number 1. And what's happening? We have fluid coming in here, fluid coming out here. No mass is lost, right? The mass coming in is the same as the mass coming out. There's no work being exchanged, so the valve isn't, there's no work happening because remember we assumed that it's frictionless, some of our ideal assumptions. And there's no heat exchange. So what do we have here? We go back to our original equation that we derived over there. 0 equals the mass N times the change in internal energy, or enthalpy. Remember, we're assuming here there's no change in mass, closed system, minus the lost or absorbed heat, minus the work input. Both of these are 0. Therefore, what we have is, and if we go from state 4 to state 1, and we evaluate this differential here, what we wind up having is M H4 minus H1. That's our system 1 balance. Now I'm going to erase this so I can keep my room, but we'll have our final result here under system 1. And I didn't reduce this far enough. So we have our mass, which can be factored out. If we divide by mass on both sides, what we're left with is 0 equals H4 minus H1, which means that H4 equals H1, which means that here, H1, that's supposed to be H4, sorry. H4 is equal to H1. We deduced that from the energy balance. So here, our most simplified term here is H4 equals H1. Now let's look at system 2. Again, we can start with our energy balance that we reduced down over there, that 0 equals M, change in enthalpy, minus the change in heat transferred, minus the change in work done to or by the system. So if we come over here and look at what's happening, we have mass coming in the system, mass coming out. We know that it's the same because we assumed a closed system. But what's happening? right? We have an evaporator. So what's going on right here? The system is doing what? It's gaining energy. Energy is being added to the system. Is there any work being done here? There's no work being done to the system or by the system. Therefore, Q is not 0 anymore, like in system 1, but work, however, is 0. So if we reduce this down, what we have is dQ is equal to M dH. So what's that saying? It's saying that all the internal energy, the change in energy for the system, is directly related to the amount of work, or excuse me, the amount of heat exchange in the exchanger. Does that make sense? What would change, what's changing between step 1 and step 2 that would change the energy? It should be directly proportional to the amount of energy that's absorbed. So we can just kind of logically deduce that we're on the right track here. And if we further kind of refine this, what we have is, and we integrate this, what we'll wind up with is dQ is equal to M dH. Right? And so the energy exchange there, which this dQ is QC, is going to be equal to M H2 minus H1. And notice I just said dQ is QC because that's how we've been labeling this QC, this heat exchange right here. Okay? So again, I'm going to erase this. I'm going to bring this up here so we can go through the last two. Just leaving it there so you can still see it. All right. Now let's look at system 3. So what are we going to do here? I'm going to start with our reduced energy balance over there. Now let's use this and evaluate system 3. So what's happening? We've got our working fluid coming in and coming out. Mass is conserved. What's happening in the system? We have work being done to the system by the compressor. So our work term is non-zero anymore. What about heat? Is there any heat being added to the system? No, there's no heat exchange here. At least we've assumed that. In practical, there may be some minor heat exchange, but in our ideal model, again, our ideal model, this is 0. So how do we reduce this now? We have the change in work is directly correlated to the change in energy of enthalpy of the system. That should make sense. The only thing happening here between state 2 and state 3 is work is being done to the system, so the change in energy of the system should be directly correlated to the change in work. If we integrate this, we'll wind up with the work, change in work, or the work input here is equal to the mass of the system times the enthalpy change. And again, this can be, we can denote that as WC if we'd like to. All right, I'll erase this. Let me write this as WC. Work with the compressor. The last system that we have to look at is system 4. And I'll write it right here. Tell you what, just for uniformity, I'll write system 4 right here. We'll do all the proofs right here. Okay. So we'll start with our reduced energy balance over there. 0 equals M dH minus dQ minus dW. And let's look at what is happening between state 3 and state 4 in our ideal system. The only thing that's happening is we're adding energy, we're taking away energy from the system. So we know that we have heat exchange going on, but there's no work being done to the system or by the system. This term is 0. If we rearrange the equation of dQ is equal to m dH. If we integrate that, we have dQ is equal to m dH. We further kind of evaluate that or put in our known terms here. We have QH is equal to m H3 minus, H4 minus H3. It's always final state minus initial state, and we're evaluating it going from this state 3 to state 4 in the workflow of the system. Transcribe that over here. Okay. So there you have it. Our energy balance around the system and around all the subsystems. Now it's important, just like in building the ideal model, don't just memorize the assumptions. I want you to understand how we got there, why we got there, because that's going to be important for you to be able to shape your mind, shape your thought process, to be able to do this on your own in other areas. I want you to take that same approach to this energy balance. How did we assume away this accumulation term? How did we assume away this term right here? The kinetic energy term. How did we assume away this term? The potential energy term. How are we just doing that? Are we just making that up to make our lives easier? Or is there some sort of valid logic that we can do that and still walk away with a good result? You need to understand that. You need to train your mind to begin to understand these things. Okay? So again, that concludes the kind of introduction to the refrigeration cycle. I hope this helps. At the next video, we will go into a detailed example of applying everything we've learned so far to an actual scenario that I've worked out in the plant. Thank you.